Well, today we're going to look at some work with the definition of the definite integral. We'll go from beginning to end on all that. But before we get to that point, we do need to introduce some summation formulas. And this first one we'll kind of develop just from the example here given. The summation of, we'll say 3, summation of a constant, if 3 goes, or if the summation goes from 1 to 5 for this constant, well, when I equals 1, the term would be 3. When I equals 2, the term will still be 3. Okay, and we'll have 3 plus 3 plus 3 plus 3 plus 3. Well, that really is the definition of multiplication. Adding a number repeatedly, we take that number and multiply it by the number of times we're adding it, and that gives us 3 times 5, or 15 in this case. So this kind of helps us generalize our next formula, our formula for the sum of a constant is that constant times the number of times that we are adding it. So the summation of a constant is that constant times n. Okay. Now, beyond that, we'll look at a couple other formulas that we'll eventually be using when we get to the definition of the definite integral. And the next one is the summation of I. Well, the summation of I turns out to be n times the quantity of n plus 1 over 2. Or summation, if I goes from 1 to 50, well, the idea there would be taking 1 plus 2 plus 3 plus 4 all the way up to 50. This formula says the summation would be 50 times 51 all divided by 2. Or whatever 25 times 51 is. Can't quite do that in my head, but that's a real quick way to add up all the numbers from 1 to 50. And we'll be using that within our definition of the definite integral. And then one more formula. Now there's more formulas than this that are out there, but these are the 3 formulas we're going to be using. Summation of I squared as I goes from 1 to n will actually equal n times the quantity n plus 1 times the quantity 2n plus 1, and then all of that divided by 6. So we'll keep those in mind. Definitely make sure you have these written down. We'll be using those in several of our definition examples. Okay, what we've been doing up to this point, we're going to pull all of this together and see how we can use this definition. We're going to be evaluating the definite integral from -1 to 2 of the function 4 minus x squared using our definition, using the limit. Now, some things we have to keep in mind. First of all, this as the mesh approaches 0, as long as we keep all of our delta x's the same value, we can change that into n approaching infinity. So, let's go ahead and see what the delta x is going to be. Okay. And we'll even state we'll make all delta x sub I equal. So what should we represent delta x sub I, or we'll just call it delta x, what should we represent that as? In our specific integral, okay, we're looking at the integral from where to where? Okay, the interval, not integral, but interval on the x-axis that we're looking at goes from -1 to 2. That would be our A to B. So how do we calculate what delta x is to equal? We say B minus A over N. Well, B minus A will give us 3. And, well, N in this case, we're going to be using N approaching infinity. So we're not going to be able to say N equal 4 or N equal 8 like we did before. We just have to leave that alone, and we're going to be using delta x as 3 over N. Okay. Questions so far? Okay, as we bring our work up to the top of the next page, we've found delta x, and we're integrating 4 minus x squared from -1 to 2, interval -1 to 2, and we're going to be summing this product, f of c sub I times our delta x. Well, next thing to look at, how do we calculate the f of c sub I? This is where it takes quite a bit more work, and it kind of goes beyond what we've looked at before. Before, we always said let n equal 4 or n equal 8, and we could fairly easily figure out what our x values were. Well, in this case, going from -1 to 2, let's just illustrate this here on the number line, and we say x sub 0 is the value of a, -1. So x sub 1, what is x sub 1 going to be represented by? It's going to be -1 plus what? To go from our first x value to the next x value in our partition, what have we been adding to the x sub 0? That's been the value of our delta x. Okay. Most of the time our delta x ended up being 1/2. So some of our intervals going from 0 to 2, our first interval was 0 then to 1/2. And the next one 1/2 to 1 and so forth. But in general, we're still going to be adding that delta x to get to x sub 1. So a plus delta x, let's write it like that. In particular, the a again is -1, and then what is our delta x this time? Okay, the 3 over n. Okay. Then what's x sub 2? What do we do to get to x sub 2? Okay. It's the x sub 1 plus another delta x. Or, if we want to stay from A, we're going from A and adding what? 2 delta x's. Okay. X sub 3, what do you think that one will be? All right, you're seeing the pattern there. A plus 3 delta x. And in particular, negative 1 plus 3 times the 3 over n. Okay. So if we generalize this, okay, we want to say what is x sub n? Or actually, not x sub n so much as, x sub I. In our summation notation, we want to write it in terms of I, not n. So x sub I is going to be what? As we kind of look at the relationship we have, the subscript of x is the same as what we're multiplying by delta x. So x sub I, the general term here, is going to be a plus I times delta x, which in our particular problem is going to be negative 1 plus I times our 3 over n. Okay. So this is major. I mean, if you can understand this, you've got the definition down. And ultimately, we're going to be using the x sub I, and there's lots of ways we can write this. I would suggest leaving it in this form, but we're going to be using this to help us with this definition. Now, x sub I, we use the x values to get the length of the rectangle. Okay, back when we were using this to estimate area under a curve, the x value, we have to use it, plug it into the function. It wasn't just the x value, but we plugged the x value into the function to get the height or length of our rectangle. Okay? And, well, in our estimation process, we used both the left endpoint or the right endpoint. Well, as we look at this, to get an idea of what the left or right endpoints would be, for the first interval, going from x sub 0 to x sub 1, the left endpoint would be x sub 0 for the first subinterval. The right endpoint would be x sub 1 for the first subinterval. Second subinterval, left endpoint would be x sub 1. So second, we use x sub 1. Or if we use the right endpoint, we would be using x sub 2 for the second subinterval. Okay. So what would make life a lot easier if we're going to be looking at f of c sub I being some sampling point of that ith interval, first interval, second interval, we want to make our notation as simple as possible. So if we're on the first interval, I want to use x sub 1 as my sampling point. Or if we're on the second interval, I want to use x sub 2 as my sampling point. So the interval that we're on, we use the right endpoint, which will allow us to say x sub 1 for the first, x sub 2 for the second, x sub 3 for the third, or in general, we use x sub I for the ith interval. You didn't know ith was a word, did you? Okay. So we're going to essentially say, let's just choose the right endpoint for our sampling point. So C sub I will in fact equal this x sub I value. And in particular, that's going to be the -1 plus I times the 3 over n. But we're not done with that. Up here, it's not just C sub I times delta x, it's f of C sub I. So we have to plug in x sub I into our function f of x to see what the actual length of our rectangle would represent. Okay? So from our definition, we'll start filling in some of the details we can. And the first detail, again, because we've let all of the delta x's be the same, we can change this mesh approaching 0 to simply n approaching infinity. Equal widths for every rectangle says, well, all of the widths will be the same. We just have to change our limit to n approaching infinity. And then we'll take the sum as I goes from 1 to n of, well, our C sub I. We said let's use the right endpoints, which would be the x sub I expression. And then delta x sub I, again with the equal widths, we can just simply say that's going to be delta x. And we know delta x is 3 over n. We'll be plugging that in here. The big part left is writing the expression of f of x sub I. We said the x sub I expression would be -1, our a plus I times delta x. Okay. But we still need to input that into our function. F of x was the 4 minus x squared. So 4 minus our input, squared, that is going to be the function we're evaluating here in the summation. Now, before we go back into our limit expression, we've got a lot of algebra to do. And that's probably the biggest part. Once we figure out what C sub I is, or x sub I, plugging it into the function, this part here is probably the most amount of work to do. And lots of details to keep track of. This is where a lot of little mistakes can happen. Okay, but let's see. First of all, looks like we better square this binomial. We'll have -1 plus I times 3 over n squared. Anytime I square a binomial, I have to rewrite it in binomial times a binomial and then FOIL. That's going to equal, well, -1 times -1 will be +1. And then we'll have minus, or -1 times I 3 over n plus another -1 times I 3 over n. So we can kind of combine that to -2 of those I times 3 over n. Okay. And then finally our last term, I times 3 over n times another I times 3 over n. We'll get I squared times 9 over n squared.
Where'd that 4 come from? 4?
This right here?
Yeah.
Okay, that's our function. Okay, so 4 minus the x squared. This right here is, again, just our x squared. So now we've got to take 4 minus that. And let's see, there's not really, we could rewrite this some different ways, but it's not really going to help. Okay. 4 minus 1, we'll get 3. And then the other terms basically just multiply the negative through. Negative times negative will have plus 2. Well, one thing we can do, let's go ahead and multiply the 2 times the 3, and that'll give us 6 over n. We'll have the I times 6 over n, and then minus, multiplying this negative through the parentheses, minus I squared times 9 over n. Okay. So this is our f of c sub I. We've got 3 terms here. We've got a constant, we've got an I term, and an I squared term. So in this case, we'll actually be using all 3 of the summation formulas. Now, not all the problems will we have to do that, but you'll see how each one of those works as we complete this one. Okay, so now back to our limits. We'll be able to put this back in here. We've got the f of c sub I, or f of x sub I, and our delta x. So plug that into our limit, and then we'll be doing a lot more algebra and finally a little bit of calculus as we apply the limit. As we put in the f of c sub I into our summation, I noticed a little mistake on my multiplying. The I times 3 over n times another I times 3 over n, we would get I squared times 9 over n squared. I think I put 9 over n, so correct that, 9 over n squared. And what did I say? The algebra here, this is going to be the easiest place to make those little mistakes, so be careful. Hopefully you'll catch those before the end of the problem and say, oh, I made some mistake somewhere, have to go back and find it. So that's your f of c sub I, and then times delta x. So we are now looking at a limit of a summation. So we're going to be calculating summation using the summation formulas that we have, and then we'll be doing some more algebra and finally taking the limit as n approaches infinity. Now, one of the summation properties we have Remember, we're summing this with respect to I, and if we have an expression times a constant, well, we can factor that constant out. This is like if we had 2 plus 3 plus 4 plus 5, all that, every term times this 3 over n. Well, we can factor the 3 over n out of that summation, and so with our summation notation, we'll have that 3 over n times, we still have these terms, and then another summation property says if we have a summation of a sum or difference, we can separate it into the summation of one term plus the summation of another or minus the summation of another. Well, that means here we can separate this into 3 different summations. And we'll have 3 over n times, well, the summation of 3 from 1 to n plus the summation of I times 6 over n minus the summation of I squared times 9 over n squared. And we'll do one more thing algebraically, and then we'll see where those summation formulas show up. The second and third summations, we can actually factor out, once again, this 6 over n, and we'll have left just the I inside the summation. And what can we do on the last one? Factor out that 9 over n squared, and we'll be taking the summation of I squared. Okay. Okay, here is where we'll be using the formulas. Summation of 3 as I goes from 1 to n, well, that's going to be what? Okay, it's that constant times whatever number of numbers we're adding together, and in this case it's just n. I guess we still have this first part to worry about. Then we have 6 over n times, what's the summation of I as I goes from 1 to n? Got that formula. N times the quantity n plus 1 all over 2. Okay. And then minus 9 over n squared times the summation of I squared. And that formula, n times n plus 1 times 2n plus 1 all over 6. So now we're finally looking at just a straightforward limit. Of course, there's lots and lots of algebra to do, lots of simplifying to do before we're going to be able to take the limit. But at this point, let's go ahead and do a little bit of simplifying here, term by term. Let's look at this term here. Fraction times another fraction. Well, we have an n divided by n. What else could we do there? 2 goes into 6, and we'll leave a 3. So with just that part there, the 3n, we're not going to have to do anything to it. But then we'll have plus 3 times n plus 1. Okay. And it looks like we're going to need to continue this top of the next page. But before we do that, we can simplify this last ugly fraction a little bit. We've got an n, cancel with one of those n's, 9 over 6, and we'll do a little more work on the top of the next page. Okay, so we've got that much. Now there's still probably this one right here we need to work on a little bit more. One thing we'll do, we'll pull the 2 out of there, and then let's go ahead and multiply this binomial times the other binomial. 2n squared plus n plus another 2n. Middle term will be a 3n, and then plus 1. And let's see, the rest of this, we'll go ahead and multiply the 3 through that part. And let's see, next up we'll multiply this through these parentheses. As we go, we'll go ahead and write down the next line. 3 over n. Now we might as well combine 3n plus 3n is 6n plus 3, and now minus, let's see, 2n would cancel, leaving n times the 3. Now make sure I'm doing this right, because I can make a little mistake as well. Proved that earlier. Then let's see, the n's will cancel in that one. We'll have a negative 9 over 2, and then finally minus 3 over 2n. I think I'm safe multiplying by 1. Well, we're still not quite done. We've got this 3 over n that needs to be multiplied by everything as well. And as we do that, let's go ahead and combine that to 3n times the 3 over n. We're almost ready to evaluate this. So 3 over n times 3n would be 9, right? N's would cancel, and then we could go ahead and combine those, but let's not. I'll show you why it's not going to matter here in just a second. 3 over n times 3 would be 9 over n. 3 over n times negative 9 over 2 would be 27 over 2n. And then 3 over n times 3 over 2n, we'll get 9 over 2n squared. And finally, we're ready to let n approach infinity. The nice thing about working with n approaching infinity, we look at this term right here, 9 over n, 9 over infinity, if you want to think of it that way, goes to what? Okay, it goes to 0. So this term will be 0. Well, this term will be 0, and this term will be 0. What about the 9? The limit of 9 as n approaches infinity is 9. Limit of a constant, no matter what n approaches, is going to be that constant. So this whole limit equals 9. And we have now completed, remember what we started with? Definite integral from -1 to 2 of 4 minus x squared dx equals 9. Now, thankfully, just like we found with the definition of the derivative, we found some shortcuts for the derivative. We're going to be looking at some shortcuts of the definite integral as well. But it is important to know where it comes from in terms of this definition. And now you'll be able to work the worksheet I gave you yesterday. You only have 4 of those, and not all of those is going to take this long, that's for sure. I chose one of the most difficult, one of the longest one as an example, just so I can show you all the different ins and outs of it. But some of the key things, again, figuring out your partition, x sub 0, x sub 1, x sub 2, and then kind of generalizing what is x sub I. Then plugging in that x sub I into your function. And then, of course, the huge mess we end up with when we put it all into the limit and the summation. Lots and lots of algebra, simplifying, get the summation of a constant and or summation of I and or summation of I squared. Plug in the formulas there. Then lots more algebra, simplifying. Finally, we calculate and we end up with our definite integral, which is 9 in this case. Okay. Well, I'll let you get to going on your definition of the definite integral worksheet, and we'll continue on with a little bit more. Tomorrow we'll do a much quicker discussion. We'll have some more time in class to work on some stuff.